Okay. So can we start today's class? So where did we stop before? Previously, we have taken electric dipole and electric field due to a dipole system. Am I right? So what is an electric dipole? It's a special category arrangement of charges. Children, keep your videos on. So electric dipole is in which fine. Two equal but opposite charges that are separated by a very small distance. And in such systems, the electric field line pattern and electric field strength pattern, they both vary one distance. They also vary with respect to certain angle. We will see that what is it. Clear? So from point to point, we expect the electric field strength to vary. And finally, we have come across the two important equations here: electric field on the axial line of a dipole and electric field on the equatorial line of a dipole. So from comparing these two equations, we can write the electric field lines on the axial line and the equatorial line. They seem to be what's a doubling. They seem to be what's a doubling. As you travel from axial line to equatorial line, it is doubling. So with this statement, if I ask you, electric field is a function, what kind of function is that with respect to angle? What kind of function is it? Did you understand my question? Electric field, what kind of function is it? Did you get my question? What kind of function it is? Is it a sinusoidal function? Can this be? The axial line and equatorial line. What kind of function it is? As the angle is increasing, what happens to the electric field strength? I want you children to take the question very carefully, think about it, then answer. என்ன kind of function? Functionsனா என்னன்னு சொல்லலாம்? Sine function, cos function, tangential function, இந்த மாதிரி நிறைய functions இருக்கு இல்லையா? அந்த மாதிரி இது என்ன function நினைக்கிறீங்க நீங்க? So I want you to draw a dipole and draw a position vector in various angles and think. As a function of theta, if I ask you, how would you draw that? Imagine I have an electric dipole here. Imagine I have an electric dipole and it is made of, electric dipole is made of, fine, let's say 2C and minus 2. 2 coulomb minus 2 coulomb. Fine. and I am going to calculate the electric field due to this dipole. So what do? I take a Gaussian surface around it. I am going to draw a Gaussian surface around it. Fine. What is the flux due to this dipole? Suppose if I take from the center, I travel 4 meters. At this point, if I try to calculate the electric flux, what would be the electric flux due to the dipole? Did you get my question? Answer. So what's the formula here? The electric flux due to a system of charges is given by, come on, according to Gauss law, from the Gauss law, the electric flux is equal to Q by epsilon naught. What is this Q? The Q is equal to the net charge enclosed by the surface. What's the net charge enclosed by the surface? 2C minus 2C. So the net charge enclosed by the surface is equal to 0. So the net flux is equal to 0. So whenever a Gaussian surface encloses a dipole, the net flux should be equal to 0. Got it? No. Noted? Yeah. So today we are going to derive another important 2-mark derivation with respect to dipoles. So this is called as electric dipole in uniform electric field. Electric dipole in uniform electric field. I am going to take a dipole and I'll keep it in electric field. What kind of electric field am I going to keep it? I am going to choose a uniform electric field, and inside that uniform electric field, I am going to keep it. Got it? Shall we go? So let's take a uniform electric field. A uniform electric field is denoted by parallel line. So whenever you see uniform electric field lines like this, either you can assume that here you have a Q positive charge, or you can expect here you have a Q negative charge. Either here you have Q positive or here you have Q negative. Got it? Any one of thing is true. It's not both. Got it? So let me go with the positive charges present here. Fine. Now I am going to keep an electric dipole in it. So let's take an electric dipole and I'm going to place the electric dipole inside. So negative charge and positive. So let's keep an electric dipole inside. Now, plus and minus charges. And what's the length of this dipole? The length of this dipole is 2a. Let me call this distance as 2a. Let me call this point as A, this point as B, where we have kept positive and negative charges. And the dipole moment of this electric dipole is traveling from the dipole moment of this dipole is traveling from negative to positive. So the P vector is in this direction. Okay. If you observe carefully, the P vector is making an angle theta with the E vector. Fine. So here theta is the angle between P vector and E vector. Noted? Can we proceed? You know very well, in any electric field, if you keep a charge, the charge will start to experience a force. And this charge is going to experience a force. What kind of force the positive charge is going to experience? It is going to experience a repulsive force in this direction. So the force experienced by the positive charge is equal to Q into E. In that direction. Similarly, this charge is also going to experience a force in this direction because this is Q plus charge will attract this negative. As a result, here there are going to be another force. So force negative is equal to Q into E. I am writing it only in the magnitude. That's why I am not substituting the plus and minus symbol here for charges. Got it? Suppose, sir, I have a line here and the force is going to pull it in this direction. Another force is going to pull this side in this direction. So technically, when this is going to happen, what happens to this whole body? The body starts to rotate. So when a dipole is kept in uniform electric field, it will start to experience a torque. Hence, it will start to rotate. So now we are going to derive torque experienced by a dipole in uniform electric field. Torque on a dipole in uniform electric. Torque on a dipole on uniform electric field. What's the formula for the torque? The formula for the torque tau is equal to force multiplied by perpendicular distance. Force multiplied by perpendicular distance. From grade 11, we know that Torque is equal to force into perpendicular distance. So now I have to find out this perpendicular distance. Can we? If I just take dotted lines, these two dotted lines are meeting at a point. This point is called as point C. So BC is the perpendicular distance. BC is the perpendicular distance. Got it? So here I can mark the angle theta. This theta and this theta are same, right? Because you take a line, you keep on drawing parallel lines, all these angles must be equal. Correct? So here I can write force is given by F is equal to Q into E, and the perpendicular distance is given by BC. Is that right? From the triangle ABC, sin theta is equal to, from this triangle, sin theta is equal to BC divided by AB. BC divided by AB. Therefore, BC is equal to AB sin theta. Therefore, perpendicular distance is equal to, what is AB, sir? AB is equal to 2A, length of the dipole. AB is equal to 2A, length of the dipole. So here I can write 2A sin theta. Noted? Copy it. Can we proceed? Ishan? So now I am going to substitute the force value and the perpendicular distance value in this equation. Therefore, the torque experienced by an electric dipole in a uniform electric field is given by, we can say, Q into E multiplied by 2A sin theta. So what is this? So we can say from dipole moment P is equal to Q into 2A. Therefore, tau is equal to P E sin theta. And in the vector form, torque tau is equal to P vector cross E vector. Okay, let me take a small digression from the previous vector form equations and this vector form equation. Previously, we had two vector form equations. One is electric force, other is electric field. So electric force vector equation and electric field vector equation. Now we have electric torque vector equation. So first equation was F vector is equal to K Q1 Q2 divided by R square into R cap. I hope you remember this. Got it? Next vector equation we have electric field vector equation. Electric field vector equation is equal to, come on sir, K into Q divided by R square into R cap. Then electric field due to axial line and equatorial line, we had same k into 2p divided by r to the power 3. And here we had the vector. So if you want to write it as a vector. Got it? And in equatorial line, E vector is equal to k into p vector divided by r cube, but this time it is in the opposite direction. Got it? இது எல்லாம் ஒரு டைப் ஆஃப் வெக்டார். ஆனா நம்ம இப்ப எழுதியிருக்கிறது இருக்கு இல்லையா, this vector. Third, the tau vector is equal to p vector cross e vector. இந்த ரெண்டு வெக்டாருக்கும் இந்த வெக்டாருக்கும் என்ன வித்தியாசம்? You know that already. Those who have learned 11th from me, they know. இந்த வெக்டாருக்கு ஒரு பேரு, இந்த வெக்டாருக்கு ஒரு பேரு. It's a deviation from the subject, but still you need to know. Yes sir, little loud. What's up? No, vector, it's a cross product all the time. Yes. இந்த வெக்டார்ஸ்க்கு என்னென்ன பேரு, இந்த வெக்டாருக்கு என்னென்ன பேரு? வெக்டார் ஃபண்டமெண்டல்ஸ்ல படிச்சிருக்கோம் நாம. இங்க இருக்காது சார் இஷான், 11th ஸ்டாண்டர்ட் ஃபர்ஸ்ட் டாபிக்ல இருக்கும். வெக்டார்ஸ் நடத்தின இல்லையா பேசிக் மேத்ல, அதுல இருக்கும். ஓகே, axial vectors and polar vectors. Vectors can be divided into two broad categories. One is polar vector, second is axial vector. புரியுதா? polar vector na enna, axial vector na enna? See, for example, f is equal to m into a. இப்படி நம்மள்ட்ட ஒரு ஈக்குவேஷன் இருக்கு. Or you can say linear momentum p is equal to m into velocity. These two are very dominantly known vector quantities. Linear momentum and force are vector quantities. Correct? And on the left hand side, force is the vector, and right hand side, who is the vector? Acceleration is the vector. And in this left hand side, who is the vector? Momentum is the vector. Right hand side, who is the vector? Velocity is the vector. That is, the direction of the force is the same direction as direction of A. Direction of P is same direction as what, sir? V. இந்த மாதிரி எங்கெங்கெல்லாம் ஒரு பேட்டர்ன் இருக்கோ அந்த மாதிரியான வெக்டார்ஸ்க்கு என்னென்ன பேரு? We call these as polar vectors. We call them as polar vectors. So the left hand side quantity is described by the direction of the right hand side quantity. And here comes a new category vector called as axial vector. Axial vectors, they always indicate the plane where the change is taking place. So here the torque is not acting in the direction of P or in the direction of E. அந்த கேஸ்ல பாருங்க, ஃபோர்ஸ் உடைய டைரக்ஷன் யாருடைய டைரக்ஷன்ல ஆக்ட் ஆகுது? ஆக்சலரேஷனோடதுல. மொமெண்டமோட டைரக்ஷன் யாருதுல ஆக்ட் ஆகுது? வெலாசிட்டியோடதுல. அப்ப இங்க லெஃப்ட் சைடுல இருக்கக்கூடிய டார்க்குடைய டைரக்ஷன் யாருடைய டைரக்ஷன்ல ஆக்ட் ஆகணும்? யூ கேன் சே எய்தர் ஒன் ஆஃப் தீஸ் ஆர் போத். நோ, இந்த ரெண்டோட டைரக்ஷன்லயுமே இருக்காது. கிராஸ் ப்ராடக்டோட இம்பார்ட்டன்ட் ப்ராப்பர்ட்டி என்னன்னா, A vector cross B vector, if you get the C vector, and all three vectors will be mutually perpendicular. All three vectors should be what, sir? Mutually perpendicular. Got it? So such vectors are called as axial vector. ஏன் சார் இது ரொம்ப இம்பார்ட்டன்ட் எனக்கு இப்போ? Now let's see what happens. So now a torque is going to act on a dipole, and this torque is going to rotate the dipole. Okay, derive பண்ணி முடிச்சிட்டீங்களா? அது a very important 2 mark derivation. You draw the diagram half mark. Torque is equal to force into perpendicular distance half mark. Calculating the perpendicular distance half mark. Final answer half mark. Got it? Key points. Noted? Fine, sir. So here we have a uniform electric field. So inside the uniform electric field, the moment when I keep a dipole, I keep an electric dipole here. Okay. This electric dipole is going to experience a torque, and this dipole is going to rotate either clockwise or anti-clockwise, depending on the direction of the electric field. Rotation can vary. So now it has rotated. Will it go for one complete rotation? Never. So this torque will rotate the dipole till the dipole gets aligned with the electric field. So the dipole gets what's aligned with the electric field. So the moment when the dipole gets aligned with the right, sir, this electric field, how will it look like? So the dipole, after getting aligned, it looks something like this. Got it? So now electric field is here and electric dipole moment is here. So this charge will experience a force in this direction, and this charge will experience a force in this direction. So there will be no torque, only there will be forces. Got it? புரியுதா? எப்போ அலைன் ஆனதுக்கு அப்புறம், அலைன் ஆனதுக்கு முன்னால only torque. Got it? புரிஞ்சுதா சார்? So now you can see what is the angular difference between E vector and P vector? You can say here P vector and E vector are E vector and P vector are what's the same direction, that is parallel. Therefore theta should be equal to 0 degree. If you substitute the value, torque tau is equal to P E sin theta. So how much should be the torque now? 0. So we call this condition as the stable equilibrium condition. Write down. We call this condition as what's a stable equilibrium condition. Under the stable equilibrium condition, net force and net torque on the charges, that is dipole, is equal to 0. So it's in the equilibrium condition. Equilibrium nala enna meaning? The net force and net torque should be equal to 0. So this condition is called stable equilibrium condition. Exactly opposite to this, we have unstable equilibrium condition. Can we draw that? This is stable equilibrium condition. Stable equilibrium condition. Now let's write unstable equilibrium condition. Can we? So as usual, you can imagine an electric field, but this time We have the plus charge here, minus charge here. So the direction of the electric field here and the direction of the dipole moment is opposite. So here you can say here P vector and E vector are anti-parallel. Or what's that? Anti-parallel. Therefore, theta is equal to 180 degree. Now also tau is equal to 0. That is, the torque experienced by a dipole becomes 0 under two conditions. For any dipole which is kept in a uniform electric field, the torque experienced by the dipole becomes 0 under two conditions. What are the two conditions? When dipole moment is parallel to electric field or the dipole moment is anti-parallel to electric field. So the dipole moment parallel to electric field condition is called as stable equilibrium condition of the dipole. When it is anti-parallel, then the condition is called as what, sir? Unstable equilibrium condition of the dipole. So under the stable and unstable equilibrium conditions, net force and net torque acting on a dipole should be equal to 0. So when do you think the net torque acting on the dipole is maximum? Yes, Sahana, you can say. When do you think that dipole experiences maximum torque? Which is perpendicular? Dipole moment. Yes, when the dipole moment is perpendicular to electric field vector, then the torque experienced by the dipole is maximum. So list out the conditions now. Torque experienced by the dipole is maximum when the dipole moment is perpendicular to field and it is 0, that is the torque is 0, then dipole moment is either parallel or anti-parallel to electric field. So the parallel condition is called as stable equilibrium condition. Anti-parallel condition is called as unstable equilibrium condition. This is how a dipole behaves in uniform electric field. This is the reason why when you take your microwave oven, inside the microwave oven, you must have seen a small tray spinning. Have you seen a microwave oven inside a tray that rotates all the time? So you put your food inside and you throw electromagnetic waves. Fine. And that electromagnetic wave produces the electric field, polarized electric field inside. And that electric field tries to rotate the water molecule because water molecule is a natural dipole. So the water molecules, they continuously rotate. In that rotation, they start to collide with each other. So heat is produced. That heat cooks the food. This is how microwave oven is capable of heating up the materials. The food materials which we keep, they get heated up. How easily they get heated up? We need polarizable materials. Natural dipoles are needed. So we found this concept. So the direction of the electric field is not going to be stable. It is going to be continuously changing. Fine, sir. That's why the tray is continuously rotating. If the tray rotates, then what will happen, sir? The tray rotates, it will keep the dipole moment not getting aligned. It will not allow the dipole moment to get aligned. Fine. In olden days, microwave ovens, the tray used to rotate. In the modern microwave ovens, the tray remains same. The electric field starts to switch direction. There are two different types of microwave ovens. Some microwave ovens, tray rotates. Some microwave ovens, they keep the electric field stable and they make the tray rotate. In some microwave ovens, they keep the tray stable, they make the field rotate. Got it? Practical application of this torque. Got idea? So this is electric dipole in uniform electric field. Now I am going to take electric dipole in non-uniform electric dipole and non-uniform electric field. Electric dipole in non-uniform electric field. So a non-uniform electric field is depicted as non-parallel lines. So from point to point, electric field strength will be varying. So here the more number of field lines are experienced. So here the strength is strong and here the strength is weak. So inside this, if you keep a dipole, this dipole will experience a torque, also a force. This will experience a torque, also a force. In that case, it experiences only a torque. So in uniform electric fields, dipoles experience only torque. In non-uniform electric field, dipoles experience torque as well as force. So in this electric field system, dipoles will never come to stable or unstable equilibrium. They would be keep oscillating. Noted? Proceed பண்ணலாமா? Fine, sir. So next 20 minutes, I want you to note down all the extra information which I have brought for you. Right? After noting them, we will solve problems from the dipole. So today I will share the PDF. The lesson is over. So now I can share the PDF. But this PDF, what I share, will contain more information than the CBSE's requirement. It will have for NEET as well as for JEE. You have to filter out what you want exactly. Got it? So here you can see the dipoles and their basics, two equal but opposite charges separated by a very small distance. And the length of the dipole and all the basic information are written here. Here note down. The SI unit of the dipole moment is Coulomb meter, or we can use another unit, dBA. So 1 dBA is equal to 3.3 into 10 power minus 30 Coulomb meter. So electric dipole is a system in which the net charge of the system is 0, but net field due to the system is non-zero. Because if you take an electric dipole, it is made of both positive and negative charges. So the sum of the positive and negative charges turn into what's a 0. Okay. And all the distances are measured from where, sir? From the center of the dipole. We derive the E at a point on the axial line. This derivation is 4. Then E at a point on the equatorial line. So finally, we can write these three information. Electric field due to a dipole on the axial line, general condition for an ideal dipole condition, general condition for the equatorial line, and ideal dipole condition. So this is for any angle. The third equation is for any angle. Note down. சொல்லி கொடுத்துருக்காங்களா சார் இது உங்க ஸ்கூல்ல? நோட் பண்ணிக்கோங்க. See, for example, children, watch the board. So I took a dipole last time. I marked this as plus charge and minus charge, and I tried to calculate a point on the axial line, for which I got this equation. Later, I draw a line perpendicularly and I mark a point on this. Then I tried calculating what's a electric field at this point. So this is called the electric field on the equatorial line. This time I am going to take a dipole and I am randomly marking a point which is not on the axial, not on the equatorial. And where is this point? Watch the board. Children, watch the board, everyone. So if this is positive charge, if this is negative charge, and the dipole moment is traveling in this direction, any measurement should be done from the center of the dipole. From the center of the dipole, I travel r distance, deviating theta angle from the direction of dipole moment. So position vector has an angle of theta with respect to p vector. Under this condition, the third equation is used. At any point around the dipole. What's the formula? Tell me. Electric field due to a dipole. Electric field due to a dipole at any point is given by, come on sir, 1 by 4 pi epsilon naught, then 2p or p? P. Fine. P by r cube into 3 cos square theta plus 1. Whole power 1. Got it? Note பண்ணிட்டீங்களா? So this is the general equation. Suppose if you take the axial line, for the axial line, what is the angular difference between P vector and R vector? Either it could be 0 or it could be 180 degree. So cos square theta will become 1 or minus 1, something like that. So if you just take it, if you take 1, cos square theta will be always 1. So when theta is equal to 0 degree, then what will happen, sir, here? E is equal to 1 by 4 pi epsilon naught P by R cube into, come on, sir, 3 into 1 plus 1 whole root. So which is nothing but 4. Root of 4 is equal to 2. So E is equal to 1 by 4 pi epsilon naught 2p by R cube. In the case வந்துச்சா நமக்கு, when the angle is equal to 0 degree, we get what? Axial line case. Suppose if you substitute the angle is equal to 90 degree, what will happen this part, sir? The whole 3 cos square theta will become 0. So only 1 will be surviving. So root of 1 is equal to 1. So this answer is going to be 1 by 4 pi epsilon naught P by R cube, which is nothing but equatorial line. Got it? So here is a common equation for all. Noted? Next we learn the dipoles in electric field. Once we learned it in the uniform field, then in non-uniform field. So dipoles in uniform and non-uniform electric fields. Note down. The net force acting on the dipole in non-uniform electric field is given by this formula: minus of dipole moment multiplied by change in electric field with respect to change in position. Change in electric field with respect to change in position, because from position to position electric field should vary. Non-uniform இல்லையா, அப்போ ஒரு இடத்துல இன்னொரு இடத்துல கண்டிப்பா வேரியபிளா தான் இருக்கணும். Noted? Noted? So work done in rotating a dipole. Take the next part. The work done in rotating a dipole. So now I am going to take a dipole and I am going to rotate it. Fine. So to do that, how much work should I do? The question. So let's imagine I have a dipole is present in uniform electric field, right? Okay, or you can just take plus and minus, the way you want. We have a dipole, and I'm going to rotate this dipole. So let's assume that I'm rotating the dipole. That. So when I rotate the dipole, what happens to the theta? Increases or decreases, depending on the direction in which I rotate the dipole. So for doing this, how much work needs to be done is the question. If I know that, if I have to rotate the dipole faster, then I have to use stronger field. If I have to rotate the dipole slower, then I have to use weaker field. This is exactly how you decide what should be the level of microwave oven that you have to set so that the heating can be sooner or later. How fast you want to heat up the material, so you keep the electric field strength so strong. And you reduce the electric field strength in your microwave oven so that the rotation becomes what, sir? Less. So the heating is low. Got it? So you need to know how much you require, how much work needs to be done in rotating the dipole. What do you know about the work done, sir? There are two types of work done: linear work done and angular work done. What's the formula of linear work done? Linear work done, W is equal to force into displacement and cos theta. Am I right? F dot S. And angular work done is equal to the equivalent of force in rotational motion is torque. Correct, sir? And the equivalent of displacement in angular motion is theta. Angular displacement theta. Got it? Got it? So here we are rotating. So we have to write work done in rotating the dipole. Work done in rotating the dipole. The title work done in rotating a dipole in uniform electric. Work done in rotating a dipole in uniform electric field. Work done W is equal to tau dot theta. You know very well, if I keep changing the angle, I have to do more and more work. So I can write work done varies when the theta varies. Work done varies when the theta varies. Correct, sir? So let this be equation number 1. Noted? From tau is equal to Te sin theta, Te sin theta, dW is equal to Pe sin theta dot sin theta dot. So now I can integrate on both sides. So left hand side integration results in W, and in the right hand side theta initial to theta final. We are going to rotate it. Theta initial to theta. You know, dipole moment is a constant for a given dipole, because this is the strength of the charge multiplied by length of the charge, length of the dipole. Am I right? So both are constants. So P is a constant. and we have assumed uniform electric field. So E is also a constant. So the P and E, they won't participate in what? Integration process. Since both are constants, they will stay away. So we can write P E into integral of sine theta dot d theta from theta initial to theta final. Noted? So what's the integral of sine theta dot d theta? Minus cos theta. Fine, sir? Which is equal to P E minus cos theta, upper limit theta final, and lower limit theta. Correct? Got it? So how do we elaborate it? Work done is equal to PE into, come on sir, minus of cos theta final minus into minus of cos theta initial. So it turns out to be work done in rotating the dipole is equal to minus of PE into cos theta final minus cos theta. Suppose if you bring this minus sign inside, work done is equal to PE into cos theta initial minus cos theta noted. From this, can you calculate how much work needs to be done in rotating a dipole from its stable equilibrium condition to unstable equilibrium condition? Calculate the work done required to rotate a dipole from stable equilibrium condition to unstable equilibrium condition. Work it. Write the question and work. So this work done on a dipole getting stored in the form of what, sir? Potential energy. So what's the formula here? From stable to unstable equilibrium, we have to rotate. So the theta initial, what is the angular difference for stable equilibrium? 0 degree. Correct? What is for unstable equilibrium? Theta final is equal to 180 degree. Because in unstable equilibrium, angle is 180 degree. ஞாபகம் இருக்கா? முன்னாடி படிச்சோம். So the work done is equal to P into E into cos of 0 degree minus cos of 180 degree. Okay. So how much it becomes? W is equal to PE into cos 0 is 1 minus cos of 180 degree is equal to cos of 180 degree is equal to minus 1. 2 times Noted? Now you can calculate unstable to stable, 30 degree to 60 degree. Any value you can calculate now, right? Can you do? What is the work done in rotating a dipole from 30 degree to 60 degree? Can you work? Work. From 30 to 60. So questions can come in. All you need to know is this formula and substitute, you get the point. Will you do that? When do you think this is going to be maximum, sir? When the cos theta is equal to 90 degree. So then cos 90 degree, the entire part will become 0. So you don't have to do any work. System will automatically rotate it. Got it? The electric field itself will rotate. You don't have to do anything. புரிஞ்சுதா? It's a dipole-dipole interaction. When you keep the two dipoles next to each other. Note down the title, dipole-dipole interaction. I have first dipole, I have second dipole. First dipole has P1 dipole moment, second dipole has P2 dipole moment. When these two dipoles are parallel to each other and they are separated by a distance r, under this condition, the force between the two dipoles is given by this formula, and the potential energy due to this system is given by this formula. This is force F is equal to K 6 times of P1 P2 divided by R to the power 4. So these two dipoles, they attract each other because positive is closer to negative, so they will try to attract each other. Got it? Not also. These are all for the NEET exam. Sometimes this question can be depicted like this: P1 vector, P2 vector, and they are separated by R distance. Okay? Noted? And the second case, P1 vector parallel to P vector, but they are not coaxial. They are just collinear. They both are facing the same direction, but not along the same line. They are facing the same direction, but not along the same line. So they are separated by a distance r. Under this condition, they repel each other because these two charges repel each other and these two charges repel each other. As a result, they repel each other. So the net force is repulsive, 1 by 4 pi epsilon naught, 3 times of P1 P2 divided by r to the power 4. Noted? And the potential energy stored in this system is given by this formula, P1 P2 divided by r cube. That is the direction of the dipole moment. In the first case and second case, they are parallel to each other, whereas in the first case, they are coaxial. In the second case, they are only collinear. Got it? Actually, they are coplanar. Technically, to take. And comes the third case, where direction of one dipole moment perpendicular to direction of the other dipole moment. So the dipole moments are perpendicular to each other. And they are separated by a distance r. Watch this. From the center of this dipole to center of this dipole moments are perpendicular to each other. Under that condition, the net force is equal to K into 3 P1 P2 divided by r to the power 4, and net potential energy is equal to 0. Why, sir? Want to scroll down? Noted? Can we proceed? Yes, sir. Take down the various units of charge. Here I have enumerated. Today, children, I am going to give this PDF to you. I want you to read the PDF. How to use the PDF, I am telling. Units of the charge. Charges have various units. So coulomb is written here. In CGS system, we have two units. One is called as the electrostatic unit. Second is called as the electromagnetic unit. So electrostatic unit ESU, 1 coulomb is equal to 3 into 10 power 9 ESU. And similarly, 1 coulomb is equal to 1 by 10th of EMU. And these are called as the app coulomb, and the previous one is called as the stat coulomb. Electrostatics la stat coulomb no, magnetism la app coulomb no. Okay, so take down these values. The practical unit of the charge is ampere hour and Faraday. So 1 ampere hour involves 3600 coulomb, whereas 1 Faraday is equal to 96,500 coulomb. ஒரு ஃபேரட்ல எத்தனை கூலம்ஸ் இருக்குது? 96,500 coulomb. So when we say 5 microcoulomb, 8 microcoulomb, our numerical problems, fine. Then we have learned about the point charges, charges on the conductor, non-conductor. I think we have covered all these. Here we have taken the area vectors for different shapes, how the area vectors are drawn. Shown the picture. Finally, coming to Gaussian space, Gauss theorem, applications of Gauss law. So, applications of Gauss law, according to CBSE syllabus, we have learned only three: linear charge distribution, planar, and charged sphere, conducting sphere. And here I have taken infinitely long conductor, a charged ring. How the charged ring has its electric field, the formula. And the field line pattern is drawn here. Got it? If I have a ring, the charged one, this is how the electric field maximum is going to be. Electric field along the x-axis given by kqx divided by x square plus r square whole power 3 by 2. Fine. The maximum value could be q divided by 6 times root 3 times pi epsilon naught r squared. So for different shapes I have given. For a fixed length of rod, a bent rod in the form of this kind of L, and only a quarter portion of a circle, half of a circle, 3/4 of a circle, and an extended rod. So for all these cases, I have given the formula in it. Got it? So for the rod, I have shown the derivation. They're all extra information. See, last time we have taken infinitely long wire. This time I am taking infinitely long metal tube, not a wire, a hollow tube. Inside it is hollow. Under that condition, what do we? Fine. If that tube is non-conducting tube, like a PVC tube, fine sir, what will be the value? So like this, I have taken a lot, and most important one of them is charged bubble. You take a soap bubble which is charged. You know, when a bubble is charged, the outermost surface, they try to repel each other, and the charges they try to stay away from each other. As the charges they try to stay away from each other, the bubble starts to expand. So the radius will increase. How long a bubble can expand, sir? As long as the surface tension allows it. You know, elongation or the inflation of a bubble depends on its surface tension. Right or wrong, sir? So here we have a formula. The pressure inside the charged bubble in terms of charge density. So using this, every year get one problem. This. Got it? So non-conducting, we are done with this. Finally, here we go. The force on a charged bubble. So let's see last part of it. Watch, children. I have an electric field. I have an electric field. Right? In this electric field, I keep a charge. Electric field, I keep a charge. Remember, I keep a charge. That means initial velocity of the charge is equal to 0 meter per second. Initial velocity of the charge is equal to how much? 0 meter per. With initial velocity 0 meter per second, if I keep a charge here, depending on the nature of the charge, if the charge is positive, then the charge will try to travel in a straight line along the field line. Nothing, something like this. you have a big Q plus, because of this big Q, you have a lot of electric field here, and you are taking a small Q, which is positive in nature. What will happen to this one, sir? It will get repelled and it will try to travel in a straight line. Right or wrong? So the electric field due to this is a line. So you can say positive charges generally travel along the field line. Suppose if you keep a negative charge, they move against the field line. So positive charges move along the field line and the negative charges move against the field line. And the trajectory. What do you mean by trajectory? Shape of the path. When electric field is uniform, the trajectory of the electric field line, they always travel in which way, sir? A straight line. Suppose if the initial velocity of the charge inside the electric field is equal to 0, fine, then the charge will travel in a straight line. Now let's assume a metal plate here. On the metal plate, you have a lot of charge. So you have electric field line emanating from this metal, the direction of the electric. Okay. Now I take a charge Q plus with some initial velocity. U is equal to some initial velocity, 8 meter per second, 10 meter per second. With that, I throw it inside. I throw it inside. So this charge is getting thrown inside. So up to some distance, this charge will travel in a straight line. Later, it will go like if this charge is a positive. Got it? Ideally, this charge should have traveled in this direction, but the charge will take a deviation and it will go. So path of the charge, the path or the trajectory of the charge is a parabola. Path of the charge is what, sir? A parabola. So basically, a static charge inside an electric field. A static charge inside an electric field travels in which way, sir? Straight line path. An accelerated charge inside an electric field travels in which way, sir? Parabolic path. Got it? So if a charge has initial velocity whose direction is perpendicular to the direction of electric field, if the V vector, this is the direction, the V vector. If V vector is perpendicular to E vector and V is not equal to 0 meter per second. V is not equal to, that is initial velocity is not equal to, under this condition, path is parabolic path. Noted? I think now you have learned a lot of equations. Now it is time for you to solve assignment problems, then a test. Okay? Brace for impact. See this? So I have taken an electron, negative charge. So the field lines are facing downward. That means on the top I have plus charge. Since the plus charge is spread over a plate, I have marked it as sigma plus. Got it? So the trajectory of the electron, the green line is the ideal line in which direction it should have gone. But red line, the red color curvature, is the path actually taken by the electron. Noted? So the displacement of this electron is given by initial velocity multiplied by time. Sum solve பண்ணணுமா வேண்டாமா? That is initial velocity along, that is displacement along x-axis is given by this formula. See, vertically it has gone some distance, deviation is taken. This y distance is given by this formula, sir. Q into E divided by 2m, Q into E divided by 2m into x squared divided by v naught squared. X squared divided by v naught squared. What is v naught, sir? Initial velocity. Noted? இதை நோட் பண்ணிக்கோ. இதை வச்சு உனக்கு ஒரு கொஸ்டின் ஒன்று தரேன். Now I will describe a question. You will try to find the answer for it. Fine? When in Rutherford's experiment, an alpha particle thrown against the gold foil, an alpha particle is thrown against the gold foil with initial kinetic energy of fine, sir, kinetic energy initial is equal to 5 joule. That's up. Actually it was the 5.5 mega electron volt. Let's take it as 5 joule. Thrown with the speed of how much, sir? 5, the kinetic energy of 5 joule. And this alpha particle travels, you know, these alpha particles, they followed multiple paths. Most of the alpha particles, they penetrated and went to the other side. A few alpha particles, they went and came back in the same path. Some alpha particles deflected like, and we are going to talk about only those deflected alpha particles. So how far did that deflected vertically? The calculation that you did. Got it? Let's suppose this E value can be taken as 4 Newton per Coulomb. For your convenience, I give you that value. Fine, sir? Work it out. Not now, do it later. So velocity of this fastly moving body at any given time. There are two types of velocities now. One velocity is actually taking the body along x-axis. So I am going to divide the velocity vector into two components. One along the x, vx, other along the y, vy. So vx and vy. So v along the x-axis is always what, sir? The initial velocity. எங்க படிச்சீங்க நீங்க அத? Projectile motion. Projectile motion along the x-axis, velocity doesn't vary. Only along the y-axis, velocity varies. So along x-axis, velocity is always the initial velocity. And along y-axis, q e t divided by mass of the body. Got it? So magnitude of the net velocity is given by root of Vx square plus Vy square. Formula is there. Direction of the V net at any given instant is given by Vy by Vx. The moment when I said I am going to post it, nobody is writing. Noted? I think with this, your first lesson is getting over, sir. Okay? So be ready for the assignment questions. So I'll keep posting the assignment questions. So before the next week, I give you 1 week to complete it. For your convenience, first 2 to 3 lessons, I will post the assignment along with the answer. Okay? One PDF as the question, other PDF as the answer. So first 2 to 3 lessons, I want you children to try, cross-verify that the answer. Any assignment question that if you find it is difficult, get back to me. Got it? So in our mentor session, that is the doubt clarification session, we will discuss that. So first 2 to 3 lessons, I will give you some relaxation of providing the answers in the first hand. Later, after 4th chapter, I will start to give only the questions. You have to work out. Later, we will discuss the questions. Then I will release the answer. Okay? Because now it is the initial stage of working out the problems. So you need some extra support. For that, I give you the answers. Got it? So positively by next week, I will add you all into the app. Once I integrate you into the app, we will start writing the test. Fine? Carry on, children. Carry on. Carry on. Good night.